Hello, and welcome to today's webinar, Detection Instrument Types and Selection, with our guests, Franz Dambo and Ian Newkirk from NUVIA. Franz is the Global Director for Health Physics and Radiation Protection at NUVIA, an international company involved with major nuclear projects. NUVIA is a designer and supplier of sophisticated radiation protection and detection instruments. With him today is Ian Newkirk. Thank you, Ian, for joining us. He's the Instrument Fleet and Sales Manager at NUVIA Canada. So before starting, we'd like to acknowledge that the spaces in which we at the Institute work in Toronto are located on the traditional territories of many nations, including the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples. Fergal Nolan National Laboratories in Saskatoon is located on Treaty 6 territory and the homeland of the Métis people. We thank them for their care of the land and pay respect to them and their ancestors. We ask that during the presentation portion that the audio and video be from the presenters only. To turn on closed captions, go to More, Language and Speech, turn on live captions. Please use the chat feature for any discussions and post questions arriving from the content in the Q&A. This will help us to find your questions for the allotted Q&A portion while allowing people to have a conversation in the chat. As the webinar is only 40 minutes in length and is immediately followed by our wellness session, time may not permit for us to answer all of them during the webinar. The answers will be posted on our website, along with a link to the video recording and a copy of the slides. This can be found under Education, Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to the Professional Association. The webinar will be a bit of a show and tell. I will give an explanation of the mechanism for each type of detector covered, gas chamber, scintillation detector, and semiconductor, and then Franz and Ian will give more detail on each, including ionization chamber, proportional counter, and Geiger-Müller detector in the gas chamber discussion. We will then talk about probes and how to select an instrument. There'll be a Q&A should there be time. Any questions on detection instruments that came in during registration or are posted in the Q&A that are not covered will be answered in a document that will be posted on our website. The final 20 minutes today will be a movement break led by Charmaine Wong of Jihong Tai Chi and Qigong of Richmond Hill, Ontario. So as a gas chamber instrument, they all basically have the same internal construction. They have a coax cylindrical cathode and a wire anode with a space between them filled with a gas. Ionizing radiation causes ions to be formed, which are then detected. There are 3 different types of gas chamber instruments, each with its own voltage range. The ionization chamber has a voltage less than 200 volts. Proportional counter is in the range of approximately 200 volts to 600 volts, and the Geiger-Müller detector is in the range of about 800 volts to 1,000 volts. So with that, we're going to let Franz and Ian talk a little bit about the detectors, about what makes each one unique and what they're used to measure and things like that. So do you guys mind starting with the ionization chamber and give a demo of them?
Yeah. Primarily, they are used for detecting dose and dose rate and exposure, and they are very good for measurement in high fields. The disadvantage is that it does not distinguish between the types of radiation. We can do a limited with the energy compensation. It's particularly used in handheld instruments and area monitors and lab units. It's a fair energy response, but it needs compensation in order to do that.
So that's with the ion chamber?
Yeah.
Yeah. So do you have one there as an example, or?
I do not think we have one here, no.
Okay. All right. So they're not quite as common as some of the other ones. Is that fair to say? As a Geiger-Müller counter, for example.
Yeah.
Yeah. All right. Now with your proportional counters, how are they different in terms of, they're kind of in between the ion chamber and the Geiger-Müller detector?
Yeah, they can detect alpha and beta with energy discrimination. And a common use for alpha, beta, low energy X-rays and count rate on spectrum. They can distinguish. They're typically in benchtop handheld alpha, beta probes, and that's a good energy response.
All right. And the Geiger-Müller detector, which is probably what the general public is most, the Geiger counters, right? Familiar with. If you don't mind explaining those a little bit.
Yeah. They are very simple, rugged, and high sensitive for locating sources. And they could be for beta, gamma, very rarely for alpha, but could be. But typically, you will see them a lot of times in your dose rate meters. And one example of that is this one here. This is a Dolmo. It works the same way as a Automess. They have a GM tube inside. You will also, if you're from Canada, you will see it similar in the radii or the gamma bot gun. So they can look different. The tube is located in the top. And normally you will actually be able to get a shine from the sides too. So that's typical for GM, the instrument, but primarily I would say for gamma dose rate, but there could be additional probes there.
All right. So in terms of these, if is there a preference in terms of energy response, that type of thing? Can you just explain energy compensation a little bit among the three instruments?
Yeah. What's very important for any instruments you use, regardless what you use, is that you need to know what you're looking for and also what energy range you are looking for. You will see the same on a Dolmo as you will see on an Automess. The energy range will always be listed on the back side of the instrument for which it is measured. And that's why it's very important that you actually use the appropriate instrument for the appropriate survey. And it's no different from when you survey something non-radioactive, like you have your smoke detector at home, that will detect things that are not radioactive as well. And there are many, many examples of where people just pick up an instrument, they buy them online on eBay, an old instrument is not calibrated, it's not properly used, and they go out and do a measurement, and they believe that they got something high. I'm going to give you an example of a very, very bad incident that happened where people from activists in Sweden did a very weird thing. They went out, they bought an instrument online, they went to a scrapyard not too far away from a nuclear power plant community, and they thought they found something. They didn't have a clue what they were measuring, they didn't have a clue what the instrument actually did, and started to measure around. They found something. They called the press. The first journalist was not very well educated either, so he started to write. They found contamination and that the power plant has illegally dumped stuff. But there was nothing at all that was coming from the power plant. It was just natural occurring radioactive material, norm. And that happens all the time. And that's why you will see, if you work in a utility, a power plant, or wherever you work in a medical setting, they have dedicated which instruments are used for what survey. So that's also very important, because you have to take in factors as what they're measuring, the size of the detector, the energy range, but you also have to do the proper checks of each instrument. Typically, the most power plants, they will call it PCBS +1. And when you bring up an instrument, the first thing you need to check is the physical integrity. That's P for physical. C is you need to check for calibration. Depending on the type of instrument, some instrument has the calibration inside programmed in, so you will see it on the screen. Some has a label on the side that will say when it's calibrated. The normal standard calibration is yearly. There might be some exceptions to that, but that's the normal calibration range it needs to be. Then you have V, and that's for battery. And typically on digital like this, it will come on when you start the instrument and also have warning signs for battery. Analog normal has a battery switch, so you switch on. And then you have a source check, and that's similar to a function check. So you normally check your instruments towards a known source. It's very common in the power plant that have special source check stations, for example.
Yeah.
And that's to make sure it's there. And you see that I mentioned +1. Can you hand me that pipe detector? When you use, for example, an external detector that has a cable connected, then you use to do a cable wiggling. And that's a part of the physical, but some utilities, they call it +1, use as an extra reminder that you need to check that it's not a loose connection. You wouldn't really feel that with our cables because we have put a little bit more money into the cabling, but I've seen a lot of instruments out in the field, the utilities that have loose connections. So that also. And part of the physical, if you use a contamination instrument, it's very good to do a light sensitivity test as part of the physical.
And one other piece of advice, or you might want to talk about a little bit, just because you brought these things up, to understand what it is you're measuring and the difference between measuring a count rate, measuring an exposure, and measuring a dose rate. That we get questions from the public all the time. And sometimes some of the questions, you could see that there's kind of a misunderstanding between what it means if you have a certain count rate versus a dose rate versus an exposure rate. And if you don't have that background, you have to kind of dig in and have a fair understanding of what it is that you're measuring, not just the radiation you're looking for.
Yes, and that's a very, very good point, and it's definitely very valid. Normally, the international standard for dose rate is sievert, but normally measures in milli or microsieverts. And that's because sievert is a large unit. North America still use the old unit, which is rem, millirem, and rem. One rem is 10 millisieverts. Whatever place you work on, don't try to convert it back and forth in your head. Always use the unit, the site or the place used, so you don't confuse yourself. That's my only advice when it comes to dose rate. I've done work on 14 different utilities, and in the beginning I want to convert everything back to what I was used to, but now I always go for the site.
Okay.
For contamination, it's very common for most contamination instruments that they will measure counts per second or counts per minute. Count per second is very common in Europe. Counts per minute is still very common in North America. But it's very simple. 60 seconds in 1 minute, so you understand that that's there. So obviously, if you have counts per minute, the values of an instrument will be much higher. Instruments like this one can also measure becquerels, but in order for this one to be accurate for the becquerels, you need then to have the correct isotope selected in the menu here.
Right.
Very common if you do technetium at a medical lab, for example, because they only have one isotope of concern. Then it's very easy to do it. And that's why it can sometimes be very, very confusing for people that they try to compare. Because if you take the measurements from this instrument in counts per second or counts per minute, you can't just take and assume that it's the same for another instrument, because the detector size will definitely make a difference how many counts per second, counts per minute you get. If you, however, have instruments that counts you becquerel for a special area, like becquerels per square centimeter, then they have already taken the efficiency and the detector size in consideration. Then you have a value that you can transfer. But it's very important, if any case, if you don't have a becquerel per a special predefined distance and it has already been assessed that way, then you can't compare instruments between them. So that's very important, because you have a small detector, it will most likely have much less counts. So there will be a lot of factors that goes in the back end. And that's why all the power plants and other utilities have a rigorous control measurement before they approve an instrument for use for that particular.
All right. And then you mentioned medical, another, like between exposure, that air kerma comes up as well, right? So knowing the difference between what it is you're measuring and then what the instrument is actually telling you is very important. Like you said, with the incident, the person didn't really understand what was being picked up and things. So when using an instrument, it's important to know what you're looking for, know what the measurements are that you're reading, and then know some of the physical characteristics. Is it telling you per centimeter squared or not? So thanks for that, Franz. So we'll go on to the next type of instrument. So in order to understand scintillation detectors and our solid state detectors, we have to do a little tiny bit of quantum, not very much. So, and it's just about orbitals and energy. So orbitals are where you have the highest probability of finding an electron, and each orbital has a specific energy level and other properties. Electrons fill up the orbitals beginning at the lowest energy state. There's only a certain number of electrons allowed to be in each orbital, and these orbitals want to be full. Scintillation detectors take advantage of the ability of electrons to move into higher energy levels when they absorb ionizing radiation and emit a photon in the visible spectrum when they drop back into a lower energy state. Molecules can also emit visible light after a similar process involving the vibration level of the molecule. So when we're looking at scintillation detectors, a similar thing, any advice or what some of their features are, why do people use them? What's the big deal with scintillation detectors?
Yeah, majority of scintillation detectors has a high sensitivity, so that's one of the factors, but also there are a lot of the scintillation detectors that actually can do spectrometry. And that's basically what you're trying to do with the spectrometric, is you're trying to identify a spectrum so you know what isotopes you have. And because every isotope have a slightly different energy range. So it depends a little bit how they're constructed and what kind of scintillation they're using.
I have a slide here showing like the internal components. So when you're talking about construction, and then as Ian's got something here, I'll go through this and then I'll shut off this so you can show it in more detail so you come up bigger on the screen. So the basic components inside is that the radiation will strike the scintillation material, and then luminescence occurs, visible light gets emitted. The light's collected on the photomultiplier cathode, which emits electrons. The electrons are multiplied by passing them through a series of diodes. The electrons are collected at the anode to produce a current pulse. And with that, I'm going to stop sharing this and let Ian, I see he's got an instrument ready to go here.
Correct, yeah, exactly. So in this case, this is a sodium iodide detector. So the detector is at the bottom. The PMT, photomultiplier tube, is up here. It has to be completely light shielded because obviously we're looking for very tiny amounts of photons. And what connects to this is the MCD. So that's basically the high voltage detector, as well as the analog front end, which is looking at what comes out. And like Franz said, there's different types. Some of them will give you an energy range. Some of them will just give you total amounts. So in this case, this one will actually tell you what you're looking at. So if you put it next to a source and you record data, you analyze that data, you can say, is it cesium, thorium, uranium?
All right, so that's pretty cool. And they come in quite a few different shapes and sizes, just like the gas chamber instruments, correct?
Yeah, 100%. So you can get 4-inch by 4-inch by 16-inch detectors. This one in particular is a 3-inch by 3-inch cylindrical. This is an example. This is actually a plastic detector, not sodium iodide, but it's in it's a 1.5 by 3 by 6 inch. But yeah, you can make them in all different shapes and sizes.
All right, so compared to the gas chamber instruments to the scintillation detectors, that I've heard that the scintillation detectors are more delicate. Would you say that's an accurate thing, that they're not as portable?
It depends the casing and what you use them for. This particular one is a plastic scintillator, but this doesn't do the spectrometric, for example. But this has some other advantages. This one measures both alpha and beta gamma. But it's very thin foil here that's zinc sulfide coated. So it's so it depends, but overall I would say yes, because most of them are fairly big. So, but it's always exceptions to the rules.
Oh, all right.
One thing to keep in mind, sodium iodide is very temperature sensitive. So you have to be careful about bringing it into cold locations. Sometimes shipping can be an issue if it's going on a plane. There's very specific temperatures that it can be exposed to, and it can crack. Plastic detectors, I would say, are more durable. Break them as easily.
And speaking of shipping, just going back to the gas chambered instruments, that it is possible to have pressurized gas chamber instruments, and those can be an issue, from what I understand, in taking them on planes. Is that correct?
Yes, that is correct, and that could be a concern. Obviously, there are special ways to transport and to prevent too much pressure, but it could be a concern. So that's something that definitely have to take in consideration before shipping.
Yes. All right. And okay, so with that, I'm going to go to the semiconductors, and we'll do a similar thing. So let me just get this slide deck back up, because I have a little animation here. Hopefully, there we go. Hopefully people can see that. It usually asks me to resume. Just 1 second. It did not. I just have to get back to the slide I was on. Sorry about that. There we go. So to understand the basic principle behind semiconductor detectors, we need to dive a little bit deeper into orbitals. In solid state physics, they call orbital energy levels shells. For an atom, the outermost shell that has electrons in it is called the valence shell. When atoms are close together, the valence shell splits. If there are a lot of the same atoms near each other, such as in a crystal, the splitting causes a band of shells called the valence band. The empty band of energies above this is called the conduction band. When electrons are in the conduction band, they can easily move through a solid. In insulators and semiconductors, between the valence and conduction band are energy states that cannot be occupied, called the band gap. In conductors, because they do not have a band gap, at room temperature, thermal energy supplies enough energy for the electrons to conduct when a voltage is applied. So they just conduct. In insulators, there's a large band gap, so electrons require a large amount of voltage to get enough energy to get electrons into the conduction band, so much so we say that they do not conduct. In semiconductors, the material is designed to make the band gap small enough that it will conduct in some situations and not others. In semiconductor detectors, the energy of the incoming radiation allows electrons to move into the conduction band. The electron moves to the positive, and then the other electrons move to fill the empty spot left behind. This causes the hole to move towards the negative. The electronics detect the electron-hole pair. These are the basic concepts that are used in several different ways to create semiconductor detectors. So again, I'm going to stop sharing the deck. I'm assuming you may have some semiconductors to show and talk about them. They're the newer, I think, of the three that we're talking about. So that's go ahead, Ian.
Yeah. So this is our NUVIA camera. So it uses a semiconductor detector. It's able to detect from a distance, depending on the size of the source. It literally works as a camera, and it will overlay the radiation on top of the image. So it uses semiconductor camera architecture, and then also an actual gamma semiconductor detection.
Now, with that, what aspect of semiconductor detectors allows for a technology like that compared to like a Geiger-Müller counter? Why wouldn't you be able to have designed that? Does it have to do with response or?
So the Geiger counter is looking at dose. So
right.
It's looking at total energy that's being absorbed into the detector. Whereas this one is actually, it's looking at what the radiation is and where it's coming from. So it's actually able to do a spectrometric analysis, whatever radiation is coming in, and it's able to locate where exactly that is.
So it's okay, Franz, I'll let you.
Yeah, so for example, if you are working in a plant, a lot of times you need to know what causes the radiation, not only that you have radiation. And by doing a spectrometric, you can get an isotope identification. So for example, this camera will not only show you where you have it, it will also identify the isotopes for you, so you know what you have. And that determines the precaution and the safety barriers you need to put in place.
So with that, is it an aspect of the semiconductor detector? So like scintillation detectors can do spectral analysis, but is their response time or their tracking of where the particles are from not as strong as with the semiconductors? Is that why that would be the preference?
Yeah, semiconductors have the better resolution, so they are more ideal for this purpose.
Okay.
But you can certain instruments you will see in certain aspects, certain instruments can overlap, but not always the same, because you need, depending what you're looking for, you might need a different resolution also.
Okay, so with them, so they have really good resolution. Are there any, and that they're able to do the spectral analysis, are there any constraints around them when they wouldn't be used?
They're small. They're much smaller than like a sodium iodide detector. So if you're looking for low levels, it's more of a challenge because you're just restricted by physics. So how many of the gamma rays, let's say, are actually hitting that detector? If you have a big piece of sodium iodide, you have much more area for that to hit, and you'll get more counts per second, so you can more quickly create a spectrum which can analyze it.
So in terms of all the detectors that we've talked about so far, are any of them impacted by strong electromagnetic fields? Where that would be a concern, like if somebody's working in an industrial center setting where there's a strong EMF background.
I would say no. There's quite a bit of testing that goes into that. So if it's a commercial product that's being sold on the market, it certainly shouldn't be affected by any EMF.
Okay, and are there any, like you had mentioned, temperature concerns with one of the detectors there? Is that a concern around semiconductors?
No.
Okay.
No.
I know
That's
that
an
there,
issue more with sodium iodide. It's not an issue with plastic detectors or with solid state detectors.
But it
Okay.
would be for germanium detectors.
yeah, the germanium ones I think have to be at liquid nitrogen temperatures, but they're mostly a lab instrument, correct?
Correct.
Yeah. Okay, so
And then, of course, the price point varies between all of the different detectors.
okay, yeah. Just
So just for an example, this one is extremely cheap.
and that's a GM, Geiger-Müller.
GM2. This one is not very cheap, but it has a lot of other features.
Right. There's some of the attendees had mentioned that the photomultiplier tubes can be impacted by EMF and magnetism. So I assume the shielding would have to be into the instrument to help deal with, well, I guess you can't shield for magnetic fields. But I guess the more electronics you have in there, the more likely it is to happen, right? Yeah. And then in terms of the semiconductors, I know with Geiger-Müller counters, in terms of high strength radiation fields, if you have something that has a lot of strength and it's in terms of saturation, what would you pick out of there if you were concerned about saturation?
Well, first of all, if you just so we go back to basic.
Right.
If you're doing high radiation field, don't use handheld instruments. Use an extension probe, a teledetector. There are plenty of them because you do not want to spend time in a high radiation field. What's important to know from all the instruments that you use, they have an upper limit and they have a lower limit. And both you will always see for a high radiation field, you will see the limit. I shouldn't say always, but most GM instruments, they have a limit where they put that you can use it. Normally, that's way above what you ever want to do in a handheld. The other thing is there's multiple ways to do remote monitoring, either by an extension probe, so you don't have to go in the radiation field too much. You can stand at the side where you shielded, for example, or you can do a teledose, which is another way of adding remote monitoring. So that's a little bit what it is. We have something because contamination monitoring is very sensitive for the background. So normally instruments saturate very quickly in a high background and you can't use a contamination meter. That's why when you're measuring for dose rates, you normally don't measure contamination. So you will either see either or. However, there are certain instruments that have different tolerance. This, for example, looks just like the other one, but I'm going to show why it's not the same. This is another instrument we have, and it's a Como 100. This one is one that goes up to a background of 40 microsieverts, where most contamination meters already get saturated. But this one can distinguish between the beta contamination in that background. And that's a little bit unique, but that's also why we have shrinked it from 170 to 100. But it's a lot of technology goes in order to be able to distinguish between the background and the contamination, because normally it's very hard to do as soon as you start to getting measurable dose rate in the background.
So understanding your background or characterizing your background is something else that you have to consider when purchasing your instrument. Okay, you had mentioned probes. I know that you had you talked about it and you had something there. So do you just mind taking a few minutes to talk about probes and why you'd need them, why you would choose to have them, what formats are around?
This particular one is an alpha, beta, gamma probe. This is what we call a pipe detector. It puts guide wheels on the side so we can center it exactly in the center of a pipe. We even have one that's small enough to go inside scaffolding tubes. It's very, very hard to measure the inside of a scaffolding tube or a pipe because the pipe and the tube provides a shielding. You don't get a good value on the outside if something is contaminated inside. So that's why you have this, for example. This is then for alpha, beta, gamma contamination. If you look at dose rate, you will most likely have a GM tube instead. And that's in order to measure dose rate. So there's a little bit different for what you're using them for. And that's what it is. What's important also to know, because certain instruments, like in this case, this is calibrated by itself, and whatever it plugs into of the instruments that are compatible with this one will just be a reader. But certain probes needs to be calibrated as a pair. So that's another aspect that also needs to be taken into consideration when choosing probes and changing probes. That not all instruments are made the same.
So what you're saying is that if they're calibrated as a pair, that if you have like a number of these instruments, you have to make sure that the sets kind of stay together?
That's correct. And that certain instruments require that because they don't have the same electronics in the probe.
Yes.
So that means that they're using things there. So in our case, this pipe detector can plug into this one, the Dolmo. It can also plug into the Como.
Right.
It can plug into the Como 100. It can even plug into a training Como. It doesn't matter. But these ones then only turns into readers. So these are then independent from that. But not all instruments are the same. So you, in certain cases, you can swap them. Certain you have to then recalibrate.
Okay, so that's something to note with the use of the instruments, to know whether the probe itself is calibrated or whether it's the instrument and probe together as a set that's calibrated. So thanks for that, Franz. I'm just thinking in terms of instrument selection, I'm going to go back to this. I'll just go through my slides, but then if you have more to add to it at the end, we'll invite that. And I think we have quite a number of people that are here that have some background as well. The chat's been going. Let me just see. There, now it's going to resume. Just 1 second. Go. So we talked about probes. So things that you have to think about in terms of your instrument selection, the general requirements of it. Is it portable? Does it need to be portable? How rugged is it? And do you require that? The ease of use and reading. Are digital scales are needed or analog scales are okay? How easy is it for someone to end up switching from a micro to a milli and not notice it? Things like that, right? Who will be using it? How familiar are they with reading instruments? The ease of servicing can be something. And speaking with Brian Bjorndal at our lab, who does our calibration service, or in charge of that, he had said that if you can't service or calibrate, there's a lot of instruments that you can purchase online now that are very cheap. But if they can't be serviced or calibrated, then you can't use them, right? They're just a parlor trick at that point. So make sure they can be serviced and that they can be calibrated. Is there a risk of them being contaminated? And if so, how easy is it to decontaminate these instruments? And how reliable are they? And that's where talking to your instrument suppliers is good. But also if you have other people that work in the industry, you can ask them about what they use and how reliable they are. But the most important thing, and I think Franz started off with it in the first section, is the type and energy of the radiation to be measured. You have to know what you're looking for, and you have to know if the instrument is capable of picking that up. And to beware of low quality instruments, because they might be tempting to buy. But remember, we can't see, hear, feel, taste, smell ionizing radiation. So you have nothing else to measure it against. If you buy an instrument that's not actually reading it, you don't know if you're reading too high or too low or just perfect. So you want to be using an instrument that is of good quality. And again, what Brian had mentioned is that, a radiation detector that costs $100 off an online site is probably not going to do the job. I think they've checked out a few of them that people have bought and tried them just to see, and they're not giving the readings anywhere near to being accurate. I don't know if you have a comment or not on that, Franz.
Yeah, actually, I have 2 comments. You probably have seen on Amazon and eBay these watches that measure gamma radiation. Some people find them really fun to have, but they are not very good at all. There's 2 reasons I definitely tell people to avoid having them. First of all, you're not supposed to put your hand close to the source if you can avoid it. You rather have something that you can stretch out. And the other way, and even better, is to use what you see on the picture there, an extension probe. So that's one of the reasons. But the other way is that the way they measure, because they don't have the same size detector, they don't have the same electronics, so that you will not get a very good reading at all from these kind of, what I would say, more fun instruments than real instruments. So that's my little comment.
Okay. What about you, Ian? Any comments on instrument selection in general?
Yeah, absolutely. I mean, even when you look at professional instrumentation, there's a wide range. So there's older. I would say Europe is a little bit more advanced. And there are a lot of advantages, like, for example, like on this detector probe, like the electronics and the calibration is all in the detector. You can connect it to multiple different devices to show the data. So yeah, I think in North America, which I assume most of our
Wait,
people
we have
watching.
we have a global audience today. We have people signed up from everywhere. So
Sure. But yeah, there's been a huge amount of development in the last decade, and there's a lot of advantages, but I think the industry needs to start looking more at like how they can create efficiencies with instrumentation as opposed to just using whatever they used in the past.
okay. And do you feel that if people reach out to companies to ask if they're not quite sure what instrument they should be using, that the individual companies are comfortable helping them select?
Yeah, I would hope so. I mean, certainly we are.
Are people, I'm just
the
wondering,
real
the companies expect you to know exactly what you're supposed to have, or is there some guidance out there?
Yeah, I think we need to be giving the industry guidance, but it is a question of what the use case is, right? Like these different instruments we've shown, they're all for very different purposes. So it depends what the use case is, what they're measuring, what the scenario is. But yeah, for sure, the instrumentation companies should be helping people find solutions.
And also, what's important also is to ask for reference places where they're used.
Right.
Because if you're coming from a norm sector, what's normally used in other norm sectors is something that's probably fits you too, and you want to know that it's done for that application. The same as if you need to look for for a nuclear power plant, then it's good to look on what other power plants across the globe is using. But
Right.
just don't focus on one market if you do a comparison, because they are, just like Ian said, could be very regional differences between countries and adaptability to new technology and what you want, because there are a lot of difference in the instrument I've seen. Certain instruments has data logging capabilities, certain doesn't. Certain are analog that you have to write everything down manually. You have to do a lot of weird things. There are also difference in certain instruments as automatic backlight in dim condition. Certain instruments don't have any backlight at all. Certain instruments has a backlight you press on, you get a few seconds of extra backlight. So that things like that you want to take in consideration, but also the versatility of an instrument. For example, if you're in a medical lab and you need to occasionally frisk something, but your primary purpose is to maybe just check your hands when you're dealing with medical technician, for example. Yeah, then this is a hand frisking station that connects to this one. Use the internal detector, but there is a sensor that measures that you place your hands in and it force you to do that. So that might be a more cost-effective way if that happens to be your use case. So is rather than getting a hand frisking station and a contamination meter. But it's all boils down to what you need is and what you're going to use them for. And that's why I always recommend people to define, first of all, what are you going to use it for? And is there other use case you have for something similar? Because in some cases, it might be much cheaper to just get an accessory to an existing instrument than to go and get separate instruments. This one can, for example, with this accessory here, turn into a smear checker. And it
Right.
used the internal detector for that. So that might be something. It's a floor boogie, but it doesn't necessarily, if you don't have that use case, then you don't need to consider that. But always define what you need before you go and buy the instrument, because if not, you're going to define your needs because some specification of an instrument. And if you only want to measure dose rate, then normal a GM tube is the instrument is the most cost-effective way you can do it for. But if you have other needs and need a spectrum, yes, then something else is the best. But
Yeah.
you always define this before you go out and do your shopping list.
And start shopping, yes. No, that's great. So the last slide here, we'll not read it out to everyone, but it'll be provided in the slide deck PDF. It's basically going through the different types in terms of the construction, the detection medium, some features on it that we described today, common uses, your advantages and disadvantages. So with that, I know that people have been asking questions and things. We'll gather up the questions and we'll write up some answers between our scientists here and Franz and Ian. We will get that along with the ones that were sent in during registration. There were about 40 questions came in. We tried to incorporate some of the answers into that. So we'll get that together. And what the next step is that we will get the video recording, we'll get that PDF with the answers out there, and we'll send that out to everyone. So with that, I am going to, we'll be skipping questions. We're going to thank Franz and Ian for being here with us today. I think it's a huge topic that it's, and what our takeaways I think today are: know your use case, know what you're looking for, think about your calibration and things like that in terms of your probes, and just try to look and see what the features are with a number of different places before you settle on any one instrument. And again, understand what it is you're measuring, because if you don't understand what you're looking for, you can end up buying the wrong type of meter, and then sometimes it's not possible to easily do the math. Like if you're doing count rates and you're supposed to be doing dose, that's not an easy thing if you don't know what isotope you're looking for, right? So I don't know, France and Ian, if you each want to leave one message for people in terms of selecting an instrument, what's best for them over and above what I just said. So Franz, what's your parting words?
Chris, I think you covered everything.
Okay. And Ian, anything that you'd like to add?
Yeah, I would just say there's a lot of new technology coming into the industry, and so don't just use what you've been using. If you're purchasing new products, go out in the market and see what's available, because there's a lot of things that will give a lot more functionality, add efficiencies, and yeah, just see what's out there.
All right. And again, if you do have a regulator, you may want to check and make sure in your regulations, again, that's one thing to check, that you're meeting what the regulator is expecting as well in terms of calibration and calibration to a certain source and things. So thank you to everyone for being here. What we are going to do now is we will move on to Charmaine Wong. This is part of our radiation safety and wellness webinar series. So what we do is we give out science-based information to everyone, and then we have a wellness portion, because it's not just about radiation protection. We have to take care of our whole body. And with that, I'll see if Charmaine is here. I'm hoping that she is. There you are.
Yep. I'm just trying to share my screen, and
I'll stop spotlighting.
Oh, right. That's the reason why. All right.
Okay. And I'll spotlight you.
Okay. So it's not yet allowing me to share for some reason. Let's just keep.
As you as a presenter.
Oh, okay. Yeah, sorry for signing in late, because there was some problem with the link. Let's see now.
Going to allow. While we're doing that, I'm just going to go back through the chat and see if there's anything I can quickly answer. Well,
so you have added me as a presenter?
Yeah, it has you as a presenter.
Oh, I can't seem to get the share button to work. I keep clicking on it, but it just jumped.
It's not.
Right.
Oh, just let me stop. Let me try this. Did that work?
See, yeah. This. Oh, okay. So this seems better.
Okay, that was my phone.
Okay, no problem. Then screen.
And you have to show yourself. See how that.
Great. Oh, is it there yet?
Yes.
Okay, there we go. All right. Thank you so much. All right, so everybody, just before we start, I just want to quickly mention again that this is just my home basement. Feel free to visit our website to check for the address of our school. Our school has a much bigger premise. It's in Richmond Hill, so we're going to have a new term coming up. So please be encouraged to check our website for the timetable for this coming up term. All right, so now before we start, let's get off the chair. And we'll just do a little bit of warm up before we actually start to do a couple of Tai Chi moves. All right, so once you are standing, try to stand tall, and then you can just step out a little bit with one of the feet, like say you step out with your left foot, and then with the feet shoulder width apart, we're gonna do the first warm up move. So interlace your fingers, the palms now facing up. Then raise the hands. When they're at the chest height, turn the palms up and stretch up. Then you unlock your fingers, open the arms bring them down the sides. And as you go down gently, do a mini squat. And then we're going to repeat that. So the arms are making big circles. So it's always helpful to breathe in as you raise your arms. And slowly breathe out as you drop the arms back down the sides and squat down a little bit. You don't have to really go low with the squat, just gently bend the knee joints and also the hip joints to go down as if you're trying to sit down on a high chair. All right, again, breathe in, breathe out. Now, so just like Tai Chi, this warm-up move is also done slowly. There are lots of reasons to go slow, which I won't have time to explain them one by one, but at least one of the benefits would be to really calm down your mind and relax your body. Just one more time. As you stand up, you want to stand tall. Feel like your spine is extended upward as you stretch up. And come back down. All right. Okay, now let's go on to the second warm-up move. We're going to do it in different circle now. This one incorporates a little bit of Tai Chi principle. So open your arms sideways with the palms facing up now. As you come down, drop the elbows as if you are pulling with your core, pulling the arms down. And then you stand up as the arms continue to come down. Bring the arms up the sides. As the hands go to the top, turn them to face each other. Turn the palms so that the palms are facing each other as you come down again. Now this one, we want to use our mind to focus on using our core, which we also call Dan Tian, to bring the elbows down as if you're trying to pull something down from the top. Pull. All right, a couple more times. Tai Chi has traditionally been practiced as an internal martial art. We use our mind to control our body a lot more. So we want to focus our mind to direct the movements of our body. One more time. Okay. All right, now that we have warmed up our body, our joints, and our heart rate a little bit, we're going to start doing a little bit more real Tai Chi, right? So first move that we're going to practice today is called cloud hands, or waving the hands like clouds floating in the sky. So the stance, the lower body for this movement is what we call the horse stance, which means, now you can step a little bit wider if you can go down a little bit lower, which means that we're gonna squat down like this as if you are trying to ride on a horse. Now make sure that you are imagining that you are actually sitting on the saddle of a horse, which means you can come back up again to relax a little bit or rest a little bit. And I'm gonna show you a side view, which means when you sit on a saddle, these hip joints need to go back and you need to imagine you are actually sitting down. Now you can come back up again. As opposed to the wrong thing would be just to bend the knees without imagining you're going to be able to sit down. All right, so now come back up again. Let's practice one more time. Sit down. If you're sitting on a saddle of a horse or sitting on an imaginary chair. One last time. So this horse stance move is really, really helpful and effective to strengthen your lower body. All right, now with the lower body figured out, let's try to practice just the hands, how the hands look like in a cloud hands movement. So first of all, we want to have one arm up, one arm down. Let's say if you have your left hand up now, the left hand would have your palm facing yourself in a semicircle. The lower hand would have the palms facing down, slightly in front of the body, slightly on the side. All right, now and then we can turn towards the left side, which is the upper hand's direction. And then we're going to switch the hands, bring the other hand up, put the left hand back down, and then we're going to turn back towards the right. And then we're going to switch again. This is cloud hands, all right? So later on, we're going to add our stance, lower body stance, and our footwork together with it. All right, now again, one more time. Just make sure that the direction that you are turning toward would be the direction that has your arm higher up. All right, so let's say if I'm going to the left side now, it would be my left hand, which is the one at the chest height. And one last time. Make sure your shoulders are relaxed as well. All right, now, so relax a little bit. Now we're going to add our stance as well as our footwork to it. This movement, cloud hands, the footwork is pretty easy. We're just going to step sideways when we're doing the horse stance. All right, so let's say I'm going to move a little bit more towards this side so that we have more space. Now we are going to move this direction, which is my right direction. And that's why I'm going to have my right hand up there. And I'm going to have the other hand down here at about waist height. All right, so now we're going to sit down a little bit to our horse stance like we did before. Then we're going to step a little bit towards the right side. And then as we move our weight to our right foot, we also turn the body. Then we're going to switch the hands, and we're going to bring the left foot back to about shoulder width apart, back to a narrower horse stance. And then we go back to the left side. Then we're going to switch our hands again. Step out. Move towards the right side. Slightly body turned. Switch the hands and step back with the left foot. After a couple more repetitions, hope you will get the hang of it. All right, so now move. Switch the hands, step. You will find that it's actually more difficult when you do the movements more slowly, because we need to really have a good balance. Now we're going to move the weight entirely to our right foot and slowly step the left foot. If you have the space, one more step, and then we go back to the opposite direction. All right, now we're going to go back to the opposite direction. You can stand up a little bit if you need a rest. Otherwise, we're going to keep going. Go to your right. To your left, sorry. And back to your right. Again, whichever direction your body is turning toward, that's the side where your hand is higher at the chest level. Again, if you feel your legs are tired, you can stand a little taller. Otherwise, challenge yourself by having a lower stance. Shoulders still relaxed, arms not stiff. All right, so we can stand back up and take a quick rest. All right, now the second move that I'm going to introduce to you is called parting wild horse's mane. The arms look like this, all right? So it's kind of like we are trying to smooth out the mane of a wild horse. That's how the arm movements look like. But before that, let's learn a different stance. Just now, the stance was called a horse stance. Now we want to learn how to do a bow stance. Now, for now, let's ignore our hands. Just let the hands be put on your hip. Then we don't need to take care of them. So now, what we want to have a bow stand look like is that we're going to have one leg at the front, the other leg at the back, almost like a lunge. Slightly different in the sense that the back leg, we want to have our toes pointed out to about maybe 30 to 45 degrees, slightly turned out the knee to match the direction of the toes, but otherwise is similar to a lunge. Now our heel should be on the floor, both heels, especially the back heel. And that's also a difference between this bow stance and a lunge. All right, so now we can actually do it together and you can follow along. Let's say you put your right foot in front, the front leg, toes point to the front, the back leg, toes point out to about 45 degrees. The weight is more on the front leg, about 60 to 70%, and the other leg would absorb about 30 to 40% of the weight. All right, so now I'm going to show you a side view. That's how it should look like. With the body not inclining forward or backward, you want to have the upper body straight up. All right, and you can switch to the other foot. That's how a bow stance look like, the bow being bow and arrow bow. So this is a bow, the front leg is a bow, back leg is an arrow. That's where it gets its name. All right. Now, with the bow stance, how are we going to step from the feet side by side forward to our bow stance? Now, so first of all, let's say we're going to step out this leg, which is my left leg here. So my right leg would become my back leg. So the back leg, the toes need to turn out to about 45 degrees. So you move your weight towards this leg, the one turned out, and then we're going to pick up the other foot, step it forward, and then we move the weight towards the front leg to form the bow stance that we just learned. And then if we want to move it back, we'll just pick up the front foot and bring it back. All right, so let's practice the other side. Turn open your left toes, which would become our hind leg with back leg. And then the other leg, we just pick it up, slowly put it at the front. And then we're going to move our weight so that it becomes like a 70-30 distribution of weight again. One more time on each side, and we're going to add our hands. So turn out your right toes, move the weight. Again, we want to do it slowly. So pick up the other foot, put it down slowly. That's where the challenge is. If you can do that, that's really good. You have a very good balance. All right, and then move the weight. And one last time on the other side. So you turn open the toes, move the weight to that foot, really balanced. Then you slowly pick up that leg, put it down slowly, heel down first, and slowly move your weight to the 70-30 distribution of weight. Okay, now we're going to add this footwork later on, but right now we're going to just do a couple of times the hands, the parting wild horse's mane. Now, first of all, we want to do what we call the hold ball, as if we are holding a ball between our two arms. A little bit onto the side, which is your left side. When my body is on this side, the left hand should be on top. And then we just open the two arms diagonally, the bottom arm going up, the upper arm going down. Let's do the same side again. Hold ball, open. Just goes up to the opposite corner, the lower hand. One last time on the same side. Lower hand goes up to the opposite corner. The upper hand just press down. Now let's do the other direction. Let's say the right hand is on top. We'll do a hold ball again. The bottom hand, being the left hand this time, is going to go to the opposite corner. And the top hand just presses down. With the palm direction, no change at all in both hands. One more time. Now one last time. You have a right whole ball with the right hand on top, left hand at the bottom. Left hand goes to the opposite corner, right hand presses down. Okay, now we're gonna add our feet, all right? So the stance, the bowl stance, that's what we just did. Now, first of all, let's say we're gonna do our left side again, all right? Left side. So when I turn my left toes out, then I would have a left whole ball. It corresponds to where your weight is. Then we're gonna pick up the right foot, step it forward. As your weight transfers to the front, we're gonna open the hands like that. All right, now we're gonna come back again and let's just repeat a couple more times. Left foot is going to be our back leg. So at the beginning, it's going to support our weight. So we have a left whole ball. Then we step forward the right foot, heel down. As we transfer our weight, we separate the two hands. Just one last time, same direction. Left foot, left whole ball. Your right leg, pick it up and step, and open your arms and shift your weight to 70-30 distribution. All right, now that's the final part would be, we're gonna do it on the other side. This time the right toes turned out. You have a right whole ball. Move your weight onto your right foot. Pick up the left foot, step forward, move, and open. One last time, two more times actually. Let's do two more times. Left, right toes, right whole ball. Step. Open. And one last time. For those who have done this before, slow down your moves, especially the weight transfer. That's how you practice your balance. All right, and then left heel. Slowly move out, relaxed and calm. All right, so I think that's the time that we have for practice, but before we move on, we're gonna just quickly do a cool down, all right? So now again, you can stand up tall again with the feet shoulder width apart. We're just gonna turn the palms up, bring them up to about waist height, turn them back to yourself, and turn the palms down towards the floor, using the two hands to make small circles in front of the waist. And we can add breathing this time. Breathe in. Breathe out. Just one more time. Breathe in. Breathe out. Okay, so with that, we conclude the practice today. Thank you very much for staying. So I'll turn it back to you, Lynn.
Thank you, Charmaine. It's always great to have you here. And thank you to everyone that was able to stay for the full time, and hopefully we'll see you again next time. Again, we'll get the recording done as soon as we can. We have quite a number of questions to answer, so that might be the limiting factor as to when we get the email out to everyone. But as soon as we have all those questions answered and ready, then we'll send out an email outlining what was on in the presentation today and a link to the video and the additional materials. So thank you.